Let me share my screen. I welcome you for the week 9 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Okay, now let's get on to the session. Okay, you're able to see my screen, right?
Yes, ma'am.
Okay, fine. Okay, so as usual, we'll have a brief recap of lectures of week 9. Okay, so lectures of week 9 started with interaction of polymers with other materials. Okay, so on that concept, lecture 62 was on compatibilizers. It was on uses. Okay, so what are the role of compatibilizers and what are the type of compatibilizers were discussed. So do we have two what are the two major types of compatibilizers that was discussed in the lecture? Do you remember, Paul?
I don't remember.
Okay, the reactive and non-reactive compatibilizers. Okay, non-reactive compatibilizers can be, your uh, kind of a block copolymer can be non-reactive compatibilizer. Okay, in reactive also, there can be some reactive end groups. Which can react with the main polymer, and they can, react and then groups can react with the main polymer and they can compatibilize, or else there is also possibility that they can form as a graft copolymer. Okay, and certain polymerization reaction can also happen in the presence of metallose and catalyst and all. Okay, that is how reactive compatibilization takes place. Okay, and this compatibilization plays a very important role in fiber treatment and sizing also. Okay, and there was a discussion on what is the surface treatment, coupling agents that are used, and how the sizing of fibers plays a very important role in polymer composite manufacturing. Okay, and what are the components for sizing of glass fibers and role of sizing in glass fibers. Okay, because your fibers shouldn't get broken when you're actually finally preparing your composite. So what are the important things that are to be present? For example, you can add a complete coupling agent, a film former. So these can be, so that there is much more interaction between the polymer and the fibers. So these kind of, and for example, in case of cellulose and all, when you're using natural fibers and all, there can be some surface treatment that can be done so that there is a better compatibilization between the fiber and the polymer when you're making the composite. Okay, uh, and then there was a discussion again on natural fibers and polymers. So cellulosic, hydrophilic fibers and hydrophobic or partially polar polymers. So how to compatibilize them, and also the concept of compatibilization in plastic waste recycling. How can it play a very vital role? Because we get a mixed plastic waste. Okay, and also there is a mixture of some particles. Okay, so how these can, compatibilization can play a very important role in the case of recycling of plastic waste. So that concept was also discussed in the lecture. Okay, next, lecture 63 was on biopolymer application. So here two major biopolymers, one was xanthan gum and the other was polyisoprene, which is nothing but your natural rubber. Right, these two were discussed, and these two were taken because in one case there are multiple interactions due to different components present in the system, and in the other case it behaves as an ideal system, right? So in case of xanthan gum, you have multiple interactions, like it has OH group, COH group. So there are a lot of ionic interactions, hydrogen bonding that is applicable. Okay, so there are intermolecular and intramolecular interaction within a single xanthan gum and between xanthan gum molecules, macromolecules, and also between xanthan gum and the solvent also. Right, so there are multiple levels of interactions that are playing in case of xanthan gum, which is used just mainly as a thickeners in food, and also it has application in oil recovery process also. Okay, and in solid state, how is the conformation, and in solution state, how are the conformation, how does ionic strength, temperature, so these aspects, causes a difference in conformation of xanthan gum. So this was discussed. And the next that material that was discussed was polyisoprene, which is nothing but a natural rubber. So here two different applications, one was elastomeric application and the other was vibration mount application. So these two were discussed also. And in both these cases, it is this segmental flexibility, segmental stretching or segmental conformation change that plays a vital role than interaction, and that is why you equate it to an ideal system, right? In case of elastomeric roll also, you're stretching of your segments and then coming back when it is released, right? That plays a role. In case of vibration amounts also, the vibration energy is taken up and it is manifested as change in segmental conformation. Okay, so this is what was discussed in lecture 63. Paul, are you there?
Yeah, ma'am.
Okay,
I'm here.
yeah, okay. You're able to recollect, right?
Yeah.
Okay, next. The next lecture was again on interaction of polymers with other materials, and here there was a discussion on adhesives and paints. Okay, so application of adhesives. What are the roles of an adhesive? What is an adhesive failure, cohesive failure of an adhesive, and then what are structural adhesive? What is the mechanism of adhesion? Right, and different adhesive formulations and all were discussed. Right, and then paints was discussed in detail. Here, what are the materials that are used for paints, and then what are the components of a paint and coating, and what is the role of polymer in paints and coatings was discussed. Okay, and then there was a discussion on water based paints, which is an associative thickener. Okay, the next set of lectures were on polymer processing and recycling techniques. Here, the lecture started with dissolution and recovery, which is based on sustainability. So here, first of all, the mechanical recycling of polymers were discussed, and what are the challenges or disadvantages that are uh, inherent in mechanical recycling, right? Because there is a degradation, or there might be chain scission, or cross-linking, additional cross-linking happening due to some material functional groups and all happening during the service life, and as well as during mechanical recycling process as well. Okay, and then the next stage was chemical recycling. So what are the processes, different chemical recycling processes, and each of these chemical recycling process, the carbon dioxide equivalent emission index, right? You cannot just say that you're developing a process as that. You have to see the sustainability aspect also, right? Because sustainability has become a big concern these days. So for example, incineration is just burning off your waste, but what happens that it leads to a lot of carbon dioxide or your greenhouse gases emission. It is not good, right? So which is not good in terms of sustainability aspect. So we should not only see about the material getting recycled, but we also have to see the sustainability aspect of it. So different processes were discussed, and what was their CO2 equivalent emission index was discussed. And then a detailed discussion on macromolecular recycling through dissolution and precipitation. This was discussed. So what are the examples of solvent that can be used? For example, LDP and HDPE and all solvent anti-solvent system can be toluene and acetone, right? So this was discussed. And then how does the dissolution rate, because since it is a macromolecule, the dissolution rate plays a very vital important role in the in this method of recycling, right? And then amorphous polymer exposed to solvent, and what are the different layers that are formed, right? It is not that it easily dissolves, so it the solvent, it interacts with the polymer, and it starts forming different layers, and finally it dissolves the polymer. So what are those different layers? Do you remember what are those different layers, Paul?
Ma'am.
Do you remember what are the different layers when a solvent is introduced to an amorphous polymer? for dissolution process? What happens to the amorphous polymer? What are the different layers that are formed? So you
Ma'am,
will
I
have,
don't remember.
okay, so you will have a glassy polymer. Okay, so that means you're
Yeah.
introducing the solvent. So once solvent starts interacting, so there will be a phase where there is a lot of solvent and polymer dissolved with a high polymer concentration in it, which is having a dissolved polymer in it. And then there will be a phase where you have, a polymer uh, which is in kind of a gel phase with the solvent. Why is this gel phase? Because you have lot of entanglements, and between these entanglements and your solvent gets permeated, so it forms a gel like layer. And then if you just move further inside through the polymer, you will have a rubbery layer, and finally you will have a glassy layer. So this is how, and slowly this gel layer starts increasing in thickness, and rubber layer starts increasing in thickness, and slowly it starts getting into the gel layer, starts getting into the solvent completely, and then the rubber layer starts going into gel layer, and then again into the uh, solvent, where the concentration of polymer starts increasing. Okay, this is how the dissolution happens in case of amorphous polymer. And then there was a discussion on anomalous diffusion process, which is quite common in case of polymers. It does not follow a Fickian diffusion, but rather a non-Fickian diffusion it follows. Okay, because
Yeah.
here in case of Fickian diffusion, your flux is proportional to the concentration gradient, and you have a constant which is a hmm, your diffusion coefficient. Whereas in case of your non-Fickian diffusion, the diffusion coefficient also becomes a function of concentration. So so it is no more a Fickian, but it's a non-Fickian diffusion. Okay, why it also becomes a function of concentration? Because especially in case of macromolecules, since you have the molecules are quite bigger, right? So obviously the complexity involved, that is what we saw the different layers in case of amorphous polymer when it's exposed to a solvent. So that is why you end up in an anomalous diffusion process. Okay, so these were discussed. uh, the next lecture was on polymerization kinetics. So what are the different polymerization operations? Like first is your polymer manufacture. So your polymer manufacture, in for example, in case of your thermoplastics, you may form the complete polymer, which can be linear or branched. Whereas in case of your thermosets or rubber, you will end up forming a resin or a pre-polymer. Okay, in polymer manufacture. And then your polymer processing techniques, it can be different molding techniques, extrusion, shaping operations and all. And then reactive processing, technique. So here, basically, especially in case of your thermosets and all, what you will do, your molding operation will be in combination with your reaction completion, because you will your in from the polymer manufacture you would have got only the resin or your pre-polymer. So during the reactive processing only you will mold, because if it is already cross-linked and it is set, you cannot further play with the polymer, or you cannot remold the polymer and all according to the trick. So for that, it should be in a pre-polymer or uncross-linked format. So after your shaping operations and all, you bring in the cross-linker, and then you shape it. You once a cross-linker is added, and then it gets to a fixed uh, you know shape. It gets set. Okay, after the cross-linking process, you will get the final thermoset. Okay, similarly in your polymer composite processing also. Okay, and then three different polymerization kinetics were discussed. One was on free radical polymerization, step growth, and living polymerization. Okay, so these kinetics were discussed in the lecture. The next lecture was on polymerization reactors. So this was on uses. So what are the modes of polymerization? What are the common industrial polymerizations? You have bulk polymerization, solution, precipitation, suspension, emulsion, and gas phase polymerization. Okay, and then what are the industrial polymerization used for different polymers? For LDPE, what type of polymerization process is used in industry? And then for HDPE, polypropylene, polystyrene, and some other examples were also PMMA and all were discussed in this lecture, right? The next lecture was on polymer processing. It was on concepts. So processing of polymeric materials. What are the unit operations involved? Right? You have mixing, shaping operations and all. And what are the tools required? Right? You may need a mold or you may need a die. Okay, for getting a particular shape. And what are the processing techniques involved, like your injection molding, blow molding, extrusion. Okay, so and then milling. Okay, and rotational molding. So these are different processing techniques that were discussed. And then how flow behavior plays a very important role. Okay, so the polymer has to flow, and then it should enter the mold, and then it takes that particular shape, and then it is solidified, right? The molten polymer flow. So the flow behavior, it plays a very vital role. And being a viscoelastic material, again, a lot of complexity brings in case of polymers. Okay, and then how the viscosity differs for a polyester. If it is a liquid crystalline polyester and a normal polyester, how does the viscosity really differed, with shear rate was discussed. And then what are the processing or properties determined by molar mass. So there was a discussion on melt flow index measurement. And finally there were discussion on dimensionless numbers like Deborah number, Weisenberg number, Reynolds number, and elasticity number. Okay, the next lecture, and the final lecture of the week was on polymer processing. This was on uses. So here two major polymer processing operations. One was extrusion and the other one was injection molding. So these two were discussed. So in extrusion, uh, there was an introduction to single and twin screw extruder, though there was a detailed discussion on single screw extruder. Okay, what are the extruder characteristics, extruder variables, right? And die opening, pressure drop. So these were all discussed. And next was on injection molding. What is the operation of an injection molding? What's the processing window for an injection molding? Okay, you cannot operate it at any temperature and any pressure. Okay, so there is a processing window. A particular range of temperature and a particular range of pressure can only be used where you have the effective production of the polymer, right? And then how do you analyze the processing operation? What are the idealized flow? You have a cuvette flow and a Poiseuille flow, right? And what are the complex geometries and phase changes happening, right? uh, and then heat and mass transfer involved in these processing operations, and then the reactions involved in these operations. So these were all discussed in lecture 69. I hope you were able to recollect all these lectures, right? You're able to recollect?
Yeah, man.
Okay,
Yeah.
okay,
Only some I am not able to recall. Most of them I am able to.
you're able to recollect. Good. Now let's get on to the practice assignment session. So following graph shows operating window for a extruder. Two speeds of extruder screw rotation, RPM1 and RPM2 are being shown, while flow characteristics for two dies, die 1 and die 2, are shown. The diameter of die 1 is d die 1, and for die 2 is d die 2 respectively. Now you have to say, whether die 1 diameter is greater than die 2 diameter, and RPM 1 is greater than RPM 2, or die 1 diameter is greater than die 2 diameter but RPM 1 is less than RPM 2, or die 1 diameter is less than die 2 diameter and RPM 1 is less than RPM 2, or die 1 diameter is less than die 2 diameter and RPM 1 is greater than RPM 2. Which of these is right? So you have a graph where your pressure drop versus flow rate is given, right? And this curve represents the die 2 curve, and this curve represents the die 1 curve, and this is RPM 1 and this is RPM 2. Now which of these is right? Which die has a higher diameter and which RPM is higher?
Die 2 has higher diameter.
Okay, why do you say so?
Wait, y-axis flow rate, man. Right. Am I right?
Yes. Y axis is flow rate.
Then die 2 will have lesser diameter.
Why do you say so? Initially, you said
Because
we,
volume will decrease, right? For the same volume, there is less diameter.
not able to get you. What are you trying to say? For the same volume, less diameter. Okay, just say on the second part. Which one, which speed is higher? Whether RPM 2 is higher or RPM 1 is higher?
RPM 2,
Okay, how do you say?
because if rotation is more, the more polymer will come out of the die.
Rotation is small, more polymer will come out of the die. Or if the rotation is large, I mean, higher the speed of rotation, more material will come out.
Mm. Yeah, when the speed RPM is more, the polymer will be more.
Okay, okay. Okay, you're saying RPM 2 is greater than RPM 1. Okay. Uh, you're saying, but die 2 is smaller than
Then,
die 1, you're saying.
yes, ma'am.
Okay. Now let's see what is the answer. It is actually die 1 is smaller than die 2. See, for example, if you take same pressure drop, I'm showing my pointer, you're able to see my pointer, right? For the same pressure
Yeah, ma'am.
drop, if you draw a line, okay, the die 2 will have a higher flow rate. So if there is a higher flow rate, that means if the diameter of the die, if it is higher, then the flow rate will be higher, right? If the opening is larger, the flow rate will be larger, right? For the same pressure drop, right? More fluid will flow through, or more polymer melt or polymer will flow through if the diameter is larger, right?
I didn't get you.
See, for example, you take a tap, okay? You're just opening the tap, okay? So the tap will have a diameter, right?
Yeah,
Okay. So when you open the tap, there are two taps. One is having a smaller diameter. The other one is having a larger diameter. So when you open the tap to the same level, both the taps, which tap will have more water coming out? The tap with the larger diameter will have more water coming out, right?
ma'am. The flow rate, are you telling the volume or this is the speed?
Flow rate is your volumetric flow rate or mass flow rate, anything you can take.
Okay,
So,
okay. So yeah, die
if you
2
have
will
a,
be
yeah,
more
if you
diameter.
have a larger diameter only, there will be a, for a same pressure drop. If you have a larger diameter only, there will be a more flow rate or more volume or more mass of material coming out per unit time, right? So that is why
Yeah, yeah.
uh, die 2 will have a larger diameter than die 1. And as you said, RPM 2, if you just look for the entire pressure drop region, the RPM 2 has a higher flow rate, right? That means the speed is higher. When you have a higher speed of rotation, so more of polymer melt can pass through the tube, right? So that is why there is a higher flow rate. Okay.
Yeah, ma'am.
Okay. Hope you got the point. Now let's go to the second question. During a polymer processing operation, Q1 is the flow rate and pressure drop requirement is delta P1. Faster production rate is required, due to which flow rate is increased by 10%. So that means Q2 is equal to 1.1 times of Q1. Based on Hagen-Poiseuille equation, for a Newtonian fluid, the pressure drop will be delta P2 is equal to 1.1 times of delta P1. For shear thinning polymer melt, the following relation will be valid. Will it be delta P2 is equal to 1.1 times of delta P1, or delta P2 is equal to 1 by 1.1 times of delta P1, or delta P2 will be greater than 1.1 times of delta P1, or delta P2 will be less than 1.1 times of delta P1. Which one of these is right? So what have they done? They have a particular flow rate Q1 and a pressure drop of delta P1. So in order to increase their production rate, what they have done is that they have increased the flow rate by 10%. That means the new flow rate is 1.1 times of uh, earlier flow rate. So based on Hagen-Poiseuille relation, if it is a Newtonian fluid that is, passing through the processing operation, then the pressure drop change will be, the new pressure drop will be 1.1 times of old pressure drop. Okay. Now they are asking, if you replace that Newtonian fluid by a shear thinning polymer melt, what will be the new pressure drop in relation to old pressure drop? Any idea? You're able to follow the
Yeah,
question.
no, no
You,
idea, ma'am.
okay, but you were able to follow the question, right?
Can you explain the question one more?
Okay. So, what they have done is that there is a particular flow rate in a particular polymer processing operation. Okay, and that particular flow rate had a particular pressure drop, delta P1. Now, they increased the flow rate. So, they wanted to increase the production rate. So, how they have done is that they have increased the flow rate. Okay, and this increases by 1.1 times of the initial flow rate. That is what is shown here. They have increased by 10%. That is nothing but 1.1 times of the initial flow rate. So this has resulted in pressure drop change. Okay, the flow rate is changed, so subsequently the pressure drop also has changed, and this change in pressure drop is given by Hagen-Poiseuille equation. Okay, and also what they have considered is a Newtonian fluid is flowing through that. Okay, so if Newtonian fluid is flowing through that, then the new pressure drop will be 1.1 times of old pressure drop. Now, what they are asking is that if I replace the Newtonian fluid by a shear thinning polymer melt, what will be the change in pressure drop? Okay. Now, you are able to understand the question?
Yeah.
Okay. Now, how do we proceed? Any thoughts?
No idea, ma'am.
Okay. I think you may not be aware of Hagen-Poiseuille equation. So, Hagen-Poiseuille equation is given by delta P by L is equal to 128 mu q by pi dt power 4. Okay, this is what is the Hagen-Poiseuille relation. Okay, now for a Newtonian, so from this relation, what can you infer? And also there is a clue given in the question also. Are you able to figure out some inference from this equation? What is the relation between the pressure drop and volumetric flow rate?
They are directly proportional.
Yes, very good. They are directly proportional. And that is why when it was a Newtonian fluid, when volumetric flow rate increased by 1.1 times, the pressure drop also increased by 1.1 time. Okay, so you got the point.
Yeah.
Now, there is another trick in this question. They have asked if you replace a Newtonian fluid by a shear thinning polymer melt. So, what do you think of a shear thinning polymer melt? What do you understand by the term shear thinning?
When shear stress is applied, the polymer shows resistance.
Is it that way? Shear thinning. Look into the equation and just think of what will be the thinning aspect in the equation. What term will help you get an idea on thinning process in this question?
No idea.
Okay. So shear thinning polymer means shear thinning material means once you apply the shear, the viscosity drops. Okay. Where do you find the viscosity term in this equation? Do we have a viscosity term?
There is no eta.
Okay. So actually the thing is that viscosity can be expressed either as mu or eta. Okay. So mu is also viscosity.
Okay.
Okay, your eta in apparent viscosity, you bring in that eta term. So mu is also your viscosity. Okay, in many of your fluid mechanics book and all, you will see mu is an expression for viscosity. So, so that means you can understand from this equation that pressure drop is proportional both to viscosity as well as to flow rate. Okay.
Floor. Yeah.
Yes. Now, the other clue is that it is a shear thinning polymer melt. So, with application of shear, your viscosity is going to drop. That means, in case of this material, your viscosity is going to decrease. Right? So, what will happen?
Yes, ma'am.
So, there is an increase in flow rate by 1.1 times. But there is a decrease in viscosity also. So, how can we relate delta P with this, with these information? All other parameters are constant. So you have to consider only delta P, mu and Q. So Q has increased by 1.1 times and mu is going to decrease. So consider these 2 points and say what will be the relation between delta P2 and delta P1.
Uh, Delta P1 will be 1.1 times delta P2
There is nothing given like that, right? Oh, okay, okay. You're saying option B.
because flow rate they changed it, right?
Yes, flow rate has become Q2 is equal to 1.1 times of Q1. Okay, and now in the shear thinning polymer melt, your mu2 is less than mu1. So one parameter has decreased and one parameter has increased by 1.1 times. So what will be the end relationship between P2 and P1?
Then it will go P2 will be going less than 1.1 times P.
You're saying option D, right?
Yeah, yeah, man.
Yes, you are right. So how is that happening is that, so according to the above relation, the pressure drop is directly related to flow rate as well as viscosity. So pressure drop delta P is directly proportional to mu and Q. Okay. So since the polymer is shear thinning, that means earlier it was Newtonian fluid and now it is a shear thinning fluid. So you can just imagine that your mu2 will be a lesser value since it is shear thinning. Okay. So we also have the new Q2 is 1.1 times of Q1. Okay. So these two parameters are changing. All the other parameters are right. That means your delta P2 will be less than 1.1 times of delta P1. So there will be an impact of 1.1 also, but it will not be equal to 1.1 times of delta P1, but it will be less than 1.1 times of delta P1 because the material is shear thinning. Right? Hope you got it.
Yeah, yes,
Okay.
ma'am.
Okay. Okay. Uh, Now the next question is, if a combination of naphthalene and sodium is used to initiate polymerization of styrene, then the most likely mechanism of polymerization is, it's a GATE 2019 question. Is it free radical polymerization or is it cationic polymerization or anionic or olefin metasynthesis, metathesis? one of these options is right? What type of mechanism of polymerization is going to happen when mm, polymerization of styrene is initiated by naphthalene and sodium? Actually, the answer is here.
Free radical.
Is it free radical? Actually, the
Because
answer
it's
is also
showing
here. Here, you can
it's
figure out the
showing
answer.
it's showing radical anion. Then bottle. Is it anionic polymerization?
Yes, it is anionic polymerization because so this is your naphthalene with sodium. It forms a radical anion. Okay. So electron transfer takes place from sodium to the naphthalene, and you will form a negative, group, I mean ion. So you end up in an anion. So this anion, this sodium naphthalenide anion is formed, and this is going to initiate your polymerization process. Okay, of styrene. Okay, that is why it is called as anionic polymerization in this case. Okay,
Yeah.
you're able to get it. Okay, good. Now next. The plot shows apparent viscosity versus shear rate of Newtonian, dilatant and pseudoplastic fluids. Based on this plot and fluid behavior as mentioned below, find out the correct combination. So 1 dilatant fluid, 2 Newtonian fluid, 3 is pseudoplastic fluid. Okay, now you have to say whether P1 is 1, P is 1, Q is 2, R is 3, or P is 3, Q is 1, R is 2, or P is 2, Q is 3, R is 1, or P is 2, Q is 1, and R is 3. Which of these is right? So you have shear rate versus apparent viscosity, and you have P, which is constant with respect to the viscosity is constant with respect to shear rate, and R where viscosity increases with shear rate, and Q where viscosity decreases with shear rate. Now you have to say whether P corresponds to dilatant fluid, Newtonian fluid, or pseudoplastic fluid, and Q corresponds to which among the three, and R corresponds to which one. This is a GATE 2018 question. At least in first.
P
Hmm,
P is 2. P is Newtonian fluid
okay, how do you
uh,
say that?
because um, stress is proportional to strain rate.
Yes, and the constant is your viscosity. So
Is-
P you're saying is Newtonian fluid. You're right. Okay. P is 2. Now, if you see among the options, there are two answers given with respect to P is 2. So, what about Q and R?
Q is pseudoplastic.
Q is pseudoplastic. Okay. And R is dilatant, you're
Is
saying.
dilated.
Okay. Okay. Now, let us see. You're right. Yes, P is Newtonian fluid. You're right. Q is pseudoplastic, and R is dilatant fluid. You're right. So, pseudoplastic nothing but shear thinning, and dilatant fluid is your shear thickening. Okay, it thickens with the application of shear rate, so that is why your viscosity is increasing. Okay, uh, so here there was a discussion in the lecture on shear rate versus shear stress for your Newtonian, Bingham plastic, pseudoplastic, and dilatant. Okay, so your pseudoplastic, this is how your shear rate versus shear stress goes about. In case of your dilatant fluid, there is an continuous increase in shear stress with respect to shear rate. Okay, and in case of Bingham plastic, what you have is that there's a jump. So there's a minimum stress that is required for the material to flow, and once the material starts flowing, then the viscosity becomes constant. Okay, then it's a linear relationship. That means the viscosity will be constant. Okay, So this is how the relationship is. Okay, you're able to follow, right? Now let's get on to
Yeah.
the next question. Okay, again here the answer is, oh sorry. Consider two plates, one made of aluminum and the other of stainless steel, bonded by an adhesive, is pulled apart. The material undergoes failure and was observed that the separated plates had some exposed metal or alloy. Identify the type of failure in the material. Okay, you have two plates. One plate is made up of aluminum, another plate is made up of stainless steel, and they both are bonded together by an adhesive. Now what we are doing is that we are pulling the plates apart. Okay, and what we are observing is that when we observe the steel plate and the aluminum plate, we see that there is some amount of exposed metal or alloy in addition to the adhesive on each plate. So you have to say whether it is adhesive failure or a cohesive failure.
It is adhesive failure.
Why do you say it is adhesive failure?
The picture.
Okay, sure, okay. But what makes you say that it is adhesive failure?
I don't know.
Okay, so you're right, it is adhesive failure. So from the picture and from the question, you can say that when the plates are pulled apart, you could observe some exposed metal or alloy. You could see that there is some exposed metal or alloy. For example, in case of aluminum, the metal there is some metal exposed, and in case of steel, there is some alloy. Steel is nothing but an alloy, right? So it is
Yes,
getting
ma'am.
exposed. So that means that in that portion there is no adhesive that has been the adhesive is not stuck properly, right? That means it is an adhesive failure. Whereas in this case, where you cannot find out any of the exposed metal or alloy, it is only the adhesive that is breaking. That means the breakage is within that adhesive material. That is why it is called as a cohesive failure. Okay. Adhesive failure, a separated plate had metal or alloy exposed as the adhesive did not stick properly to the material. Okay. You're able to follow, right?
Yeah, ma'am.
Okay. Next. In addition to solvent diffusion, segmental relaxation, disentanglement, the dissolution of semicrystalline polymer also involves. We just saw, what happens, when you have to dissolve an amorphous polymer, right? We saw different stages, right? Where you have a portion where you have a polymer concentration high along with solvent, then a gel like phase with entanglements and solvent, and then a rubbery phase, and then the glassy polymer also. Now if you have, in place of a glassy polymer, you have a, or an amorphous polymer, you have a semicrystalline polymer. What additional thing has to happen for the semicrystalline polymer to be dissolved into the solvent?
Unfolding of crystal.
Yes, perfect. Chain unfolding also. So the crystal has to unfold the chain, and then again you have your segmental relaxation, disentanglement, solvent diffusion, everything happening to dissolve the semicrystalline polymer. You were perfect. Now let's see the next question. Rate of polymerization in anionic polymerization is it given by Rp is equal to Kp into Ki by Kt whole power zero point 0.5 Ci power zero point 0.5 Cm, or is it Rp is equal to Kp into COH square, or is it Rp is equal to Kp into Cm, or is it Rp is equal to Kp into concentration of COOH square into Cm? Which of these is the right answer?
Mm,
Do you remember any concept that was discussed on anionic polymerization in one of the earliest lectures? And also in this lecture also it was given, there was one point Anionic polymerization is also called as
And I think leaving polymerization. Uh,
living polymerization, right?
yes, ma'am.
So what causes the stoppage of the reaction in case of anionic polymerization?
Can you
When the,
repeat, ma'am?
huh? No, when does the anionic
Can you,
polymerization reaction end?
when the monomer is exhausted,
Yes, that means what is the deciding material for anionic polymerization reaction?
the initiation complex.
Is it the initiation complex, or just now you told something, right? Once a monomer gets over, the reaction stops. That means your monomer concentration is what is going to decide your anionic polymerization reaction, right?
But initiator concentration also plays a role, right?
No, initiator is available, okay, but in the same initiator you can start because you start going to attach your monomers to the initiator, okay. That is how it is going to happen. That is what an equivalence was drawn between a box and balls, right? So in the same box you can add all the balls also, and you have multiple box also, you can add all the balls available. So it is the number of balls that is going to decide it. It is the concentration of monomer that is going to decide, okay. Always the rate
Yeah.
determining step, which is happening the slowest, or which is the most crucial, will be involved in the rate of reaction, okay. So that means the monomer concentration is what is very critical here. That means among the given one, the relation is rp is equal to kp into cm is what is for the anionic polymerization. The first one actually corresponds to your which polymerization reaction? Free radical.
The free radical. Yeah.
Yes. Okay. And the second one actually corresponds to your step growth polymerization under the condition that there is an equimolar concentration of your glycol and acid. Okay. If both are of same concentration, then your rate of polymerization is equal to Kp into either concentration of OH functional group to the power 2 or concentration of COOH functional group to the power 2. Okay. Hope
Yeah.
you got, yeah, hope you got it. And the last one is just some dummy. Okay. Next. This is a GATE 2021 question. Particular free radical polymerization reaction process yields a polymer with a number averaged degree of polymerization xn bar equal to 100. The monomer concentration is doubled and the initiator concentration is increased by 4 times. Assuming that all the rate coefficients and other parameters remain unchanged, then the value of xn bar, that is the degree of polymerization, will be what? There is also another question. Also, what will happen to the rate of polymerization when there is a increase in concentration of the monomer, which is doubled, and initiator is increased by 4 times? So two questions are asked. One is what happens to the degree of polymerization. The second is what happens to the rate of polymerization. For both the cases, what is the condition is that the concentration of monomer is doubled and the concentration of initiator is increased by 4 times. So how do you proceed?
We first write the equation for x bar.
Do
Uh,
you remember the equation?
no.
Okay. And similarly, you will be using the rate of reaction equation for finding out what will happen to the rate of polymerization. Okay. Now, so given free radical polymerization, Xn bar under the condition 1 is 100, and they have given that concentration of monomer in the case 2 is 2 times the monomer concentration in case 1, and concentration of initiator in case 2 is 4 times the concentration of initiator in case 1. Okay, so Cm2 is equal to 2 times Cm1, and Ci2 is equal to 4 times Ci1, and then Xn bar 2 we have to find out. So the relation is Xn bar is equal to Kp into Cm by 2 times into square root of Ki Kt into Ci. Okay, they have given that all other rate coefficients and parameters remain unchanged. So Kp is going to be constant both in case 1 and case 2. Ki, Kt also the same case. That means you can cancel those, right? You can eliminate
Yeah,
those. You can eliminate those. Not cancel, you can eliminate those. And then you can write as a proportionality, right? Xn bar is proportional to Cm by square root of Ci. Right? Now Xn2 bar by Xn1 bar, right, is equal to Cm2 by square root of Ci2, and divided by Cm1 divided by square root of Ci1. So you just have to incorporate what is the relation between Cm2 and Cm1, Ci2 and Ci1. And once you incorporate, you will get that your average degree of polymerization does not change, right? Because here it becomes 2 times of Cm1, and here it becomes again 4 times of Ci1, and when it comes out of the root 2. So these two gets cancelled, and then numerator and denominator are the other, all the other terms gets cancelled. So your Xn2 bar is equal to Xn1 bar, that is equal to 100. Now we have to find out what will happen to the rate of polymerization. So rate of polymerization we just saw in the previous question, right? This is
yeah,
the A is the relationship. Now calculate and say what will happen to the rate of polymerization in case 2, when initiator concentration is increased by 4 times and monomer concentration is increased by 2 times. Calculate and say Rp2 by Rp1, or how does Rp2 and Rp1 relate? I showed the answer also, but in any case just calculate and say. Are you trying the calculation?
yeah.
Okay, just do it.
It is 4 times RP1
Yes. How do you say it is 4 times?
because it square root of initiator times concentration of mono.
Okay. Yes, you are right. So since it is square root of initiator, so initiator is increased by 4 times. So square root of 4 into Ci 1. So that is that you will end up 4 coming out of the square root, you will get 2. So 2 root of Ci1 into 2 times of Cm1 by root of Ci1 into Cm1. That you will end up 4. So the Rp2 is 4 times Rp1. Okay. Now identify if the statement is correct. Good wet out and dispersion are essential for composite fabrication. Is it true? Do we need a good wet out and dispersion for
Yeah, it's true.
yes, you are right. The statement is correct. So this was discussed under incompatibilizes the role of sizing in glass fibers. So you need a good run out, high strand integrity and good wet out. So there should be a good wetting of the fiber with the polymer melt. Okay, so that it is uniformly dispersed and it forms a proper structure. So good wet out is essential, and also it should have a predictability of curing and nucleation also, because obviously the presence of fiber will affect the curing and nucleation of the polymer melt, and that should be predictable as well. Okay, so that you are ending up with the required structure or the required degree of crystallization once it cures off in case of semicrystalline poly. Next, in xanthan gum, the extended chain with helical conformation in solid state is due to what causes a helical conformation and extended chain in case of solid state of xanthan gum.
A hydrogen bond.
Yes, you are right. Hydrogen bonding. So hydrogen bonding causes the macromolecule to have an extended helical conformation. Okay. And what do we have hydrogen bonding? You have lot of this OH groups and COH group and all. So that the hydrogen bonding is between this OH group and all. Okay. So it's that is what is given. That causes an intramolecular and intermolecular hydrogen bonding. Next question. In associative thickeners, the association is through sticky ends made of dash blocks. What kind of blocks do these associative thickeners have?
A hydrophobic.
Yes, they have
Hydrophobic.
hydrophobic. So these associated thickeners they are hydrophobically modified ethoxylated urethanes. So these hydrophobic ends they are also called as sticky ends. And they associate through the sticky ends as you can see. So they can form a particle or they can form a micelle also. Okay. And they can associate with another hydrophobic polymer particles or between two of these for polymeric group itself between these due to the interaction between the hydrophobic groups. Okay. Next question. Weissenberg number is given by sorry.
I don't know.
Okay. It has some relevance to some rate and time. Mm. Any idea?
No idea.
Okay, Weissenberg number is given by your strain rate into your relaxation time. Okay, material relaxation time and strain rate. Okay, this is how the relationship is. It's either a velocity into your relaxation time by your length, uh, or, or it's nothing but velocity by length. You can define it as a strain rate as well. Okay, and lambda is your relaxation time. Okay, and Reynolds number is inertial force by viscous forces, and your elasticity number is given by your Weissenberg number divided by your Reynolds number. So these are all some important dimensionless number, especially when it comes to polymer processing. Okay. Now next, in suspension polymerization, wide distribution of monomer droplets leads to dash molar mass distribution. What happens in case of suspension polymerization? When the droplet size distribution is very wide. That means you have a mixture of different sized droplets.
No idea.
Okay. Actually, it leads to broader molar mass distribution. So in case of suspension polymerization, the monomer droplets acts as reactor. Okay, the monomer droplets are suspended in a solvent in case of suspension polymerization. And if this droplet sizes are going to vary drastically and if they are going to have a wide distribution, okay. So for example, from 1 micrometer to 100 micrometer, there are different sized droplets. Okay. That means in that droplet is going to uh, be as a act as a reactor and your polymer is going to form in that droplet. So that means a smaller droplet will have a smaller molar mass. A larger droplet will end up in a polymer with a larger molar mass. Since the distribution is very large, again your polymer molar mass will also be, the distribution will also be very broad. Okay, hope you are able to recollect. In case of emulsion polymerization, this is further fine tuned because of There, in case of emulsion polymerization, your micelles, the surfactant micelles act as a reactor. Okay, which you can, the size of the micelles can be controlled much more efficiently than your droplets in case of suspension polymerization. Okay, you are able to follow?
Yeah.
Okay.
Yeah.
Okay. Next question. A polymeric material of density 0.9 gram per centimeter cube and melt volume of 10 centimeter cube in an extruder has a residence time of 100 seconds. The output of the extruder is dash kilogram per hour. So how do you find the output of the extruder? They have given material density, they have given the melt volume, and they have given the residence time.
No idea.
Okay. Now let's see. So they have given the density of the polymer as 0.9 gram per centimeter cube. They have given volume 10 centimeter cube. Right? Can you find mass from density and volume?
Yeah. Uh, Mass
Wo-
equal to density times volume.
Okay. Right. How do you find the mass flow rate? What is mass flow rate?
No idea.
Mass flowing per unit time is your mass flow rate. Right? Rate means something with respect to time. Right? So mass with respect to time. So mass flowing per unit time. So it will have a unit of mass divided by time. So now can we find out what will be the mass flow rate in the system? Can we find out the mass flow rate? You said
Mm.
your density multiplied by volume will give you mass. And I told you that mass flow rate is nothing but mass flowing per unit time. Now we have density, volume, and also time also they have given. Now find out the mass flow rate. That is going to be the output of the extruder. Can you calculate
Then
and
it
say?
then it will be 0.09 gram per second.
Okay. So what have they asked? The output of the extruder in kilogram per hour. You said gram per second. Now we have to convert that to kilogram per hour.
That's
Are you trying?
yeah, ma'am. Ma'am, I got it as 2.5 into 10 raised to minus 8.
Okay. Now let's see what is the answer. So output of the extruder in kilogram per hour is nothing but your mass flow rate from the extruder. So rho V into T. Mass is rho into V, and mass flow rate is going to be rho V divided by T. Okay, that is equal to 0.9 into 10 by 100. So you will get 0.09 gram per second. So you were right till this. Now you have to convert your gram per second to kilogram per hour. So you have to convert second to hour. That means you have to divide by 3600. So already second is in denominator. So dividing by 3600, it will go to numerator. So 0.09 into 3600. And gram to kilogram conversion is into 10 power minus 3. That is nothing but divided by 1000. So you will get a 0.324 kilogram per hour. You got it?
No, man. I got another answer.
Ah, no. You are able to get the logic right now.
Yeah.
Convert
Logic I
unit.
got.
Yeah, unit conversion. You have to be very critical. Now next, melt flow index of a polymer depends on its molecular weight and melt viscosity. Select the correct relation from the following. So melt flow index is it directly proportional to, sorry, is it inversely proportional to molecular weight, or is it directly proportional to molecular weight? And is it inversely proportional to viscosity or directly proportional to viscosity? Which of these is right?
Option number C,
It is inversely proportional to viscosity.
to
Okay.
viscosity.
What about molecular weight?
It will be, that will be also inversely proportional.
Okay, you are right. So melt flow index will be inversely proportional to molecular weight and inversely proportional to viscosity. The molecular weight is higher, then your flow will be lesser. And similarly, if your viscosity is higher, the flow will be lesser, and vice versa. So this is how it happens. So uh, your melt flow index increases, your mass flow rate decreases. And if your melt flow index increases, your fluidity increases. Whereas if your melt flow index increases, your material properties like impact strength, elongation, Paris sag resistance, these and all decreases. Okay, this is a relationship. Next, an extruder is supplied with 40 kilowatt of power. The mass flow rate of a polymer through the extruder is 240 kilogram per hour, and the specific heat capacity of the polymer is 4 kilojoule per kg per Kelvin. The maximum possible temperature rise in the polymer is it 150 Kelvin, or is it 100 Kelvin, or is it 600 Kelvin, or is it 0? So they've given power of an extruder is 40 kilowatt. They've given mass flow rate as 240 kilogram per hour. Specific heat capacity of the polymer is 4 kilojoule per kg Kelvin. Now they have asked what is the temperature rise? How do you do it? Any thoughts?
I know an idea.
Let's see how to solve this problem. Given power is 40 kilowatt, that is nothing but 40,000 watts. Mass flow rate of the polymer is 240 kg per hour. So you are converting into SI units. So 240 by 3600 kg per second. You are converting hours to second. That is why you are multiplying the denominator 3600. Okay. Specific heat capacity C is 4 kilojoule per kg per Kelvin. That is nothing but 4000 joule per kg per Kelvin. Now your power can be written as mass flow rate into specific heat capacity into change in temperature. Okay. This you are deriving by heat is equal to MCP delta T from your basic thermodynamics. So here, since it is a mass flow rate, so your heat or work done per unit time will give you your power. So that is why you get arrive at this relation P is equal to m dot into C into delta T. So delta T you have P by m dot into C. Now you have the relation and you have all other parameters except delta T. So can you find out delta T?
Yeah.
Have you done the
Well, ma'am,
calculation? Mm.
I got 150 Kelvin.
Okay, you are right. So delta T is equal to power by mass flow rate into specific heat. So 40,000 divided by 240 by 3,600 into 4,000. So you will get delta T is 150 Kelvin. So the maximum possible temperature rise in the polymer is 150 Kelvin. Okay. Now next, a rubber compound is made by mixing functional additives with rubber using, is it done using 2-roll mill or 3-roll carender, or is it compression molding machine, or is it thermoforming machine? Which of these processing equipment is used for mixing an additive with rubber to form a rubber compound? This was discussed in the lecture Polymer Processing 1 when different processing techniques were discussed. Any idea?
Option A.
2-roll mill, you're saying? You're right, it's 2-roll mill. This was discussed in the lecture where
Yeah.
different processing techniques were introduced. That time it was told. Okay, now next question. This is a GATE 2009 question. The previous question was also GATE 2010 question. This is a GATE 2009 question. So, pair the items in column 1 with those in the column 2. So, column 1 you have some processing step, and for column 2 you have certain items. Okay, what are the processing steps? Rotational molding, extrusion, reaction injection molding, blow molding. And items in column 2 are polyurethane, use of a gas, centrifugal force, twin screw. So which will match with what?
Ma'am, I can't see your screen. Sir, it is blacked out.
Now you are able to see my screen.
No, ma'am.
No, now you are able to see my face, right?
Ma'am, I can't see your face and screen.
No, nothing you are able to. 1 second.
I think it's my network issue.
Okay, 1 second. I've just stopped sharing. I am sharing again. Now tell me if you are able to see my screen. Now you are able to see?
No, ma'am.
Okay.
It's my network issue.
Okay. Okay. Let me read through the question again. So, the column 1 has 4 different things: rotational molding, extrusion, reaction injection molding, blow molding. Okay. And column 2 has polyurethane, use of a gas, centrifugal force, twin screw. So, which one will match with what? You can make a note. Did you make a note? Since you're not able to see my screen.
Can you repeat the techniques again?
Yes. Rotational molding, extrusion, reaction injection molding, blow molding.
And on the other side, left, right
Polyurethane,
hand side.
polyurethane, use of a gas, centrifugal force, twin screw.
Uh,
Yeah. At least one thing you could say it very easily. When we were discussing the brief recap of lectures on polymer processing, we discussed one thing very clearly. What was that?
extrusion for
Yeah,
twin screw.
twin screw. Yes, you're right. What about the other three?
Blow molding, use of gas.
Okay.
Reaction injection for a polyurethane.
Okay.
And rotational molding for centrifugal force.
Yes, you're perfect. So your rotational molding, it uses a centrifugal force. Okay. And extrusion, you have twin screw. You have twin screw extruder and single screw extruder. So here they have given twin screw, so that matches with extrusion. Next, reaction injection molding, polyurethanes. They use very commonly this reaction injection molding. Finally, blow molding, obviously you use a gas. In fact, blowing agents, azocarbamide was asked, a question on azocarbamide was asked in one of the earlier assignments, I remember. It is used as a blowing agents, right? Where it produces gas through reaction, right? You end up in different gases, which helps in blowing, right? For forming some foamed polymer. Okay. So now let's move on to the last and final question of the week. Here again, this is again match the following. You have certain materials and certain processing materials on the left hand side and processing technique on the right hand side. So materials are water tank, chair, cable. You're making a note of it?
Yeah.
Okay, water tank, chair and cable. And right hand side items are injection molding, extrusion, rotation molding.
Can you repeat?
Injection molding, extrusion, rotational molding.
Water tank for rotation molding.
Okay. Chair.
A table, a
Ah,
chair for injection molding,
okay.
and table for extrusion.
Yeah, it's not table, it's cable.
A cable.
Yeah, yeah, you are right. So it's actually water tank, rotational molding, chair is injection molding, and cable is extrusion. Okay. So rotation molding, this was discussed in class, where your water tanks are all preferably manufactured using rotational molding, where you fill in the polymer powder, and then you heat it in a rotating chamber. It rotates and then it spreads according to the mold size, and then later it is cooled down and the mold is released. The product is released from the mold. And extruder, you have a die through which the material passes through. You have different units, and then finally it passes through the die, so cables can be formed through extrusion. And in injection molding, you will have the mold where complex mold can be uh, there in injection molding. So chair is one of the complex shapes, so chair can be produced by injection molding. Okay. That's it with the session.
Yeah.
So sorry, one second. So, any other questions? Paul, do you have any other questions? Paul, are you there?
Ma'am, yes.
Any other questions?
No questions, ma'am.
You don't have any doubts. Okay, so you were clear with the recap of lecture and the practice assignment, right?
Yeah,
Okay. So if there are no other further doubts, then we can officially end the session. Okay?
yeah, yeah.
Okay.
Thank you, ma'am.
Yeah. Thank you.